Hey, welcome back, physics students, to Rapid Review for Honors Physics. Today I have for you a special presentation. What makes it special is this is the only new presentation I'm creating here for this YouTube series. I noticed as I looked at all of the topics that I've been covering, there's a big gap when we get to projectiles. And I recognize that the reason for that is in my classroom, most of the learning on projectiles was done either experimentally with a series of labs or through pretty substantial homework sets, because it takes a lot of practice to do, just to learn how to do the calculations for projectiles. So I felt it was missing from this series, and I created a special presentation here for you for this YouTube series so that I get to say a few what I think are kind of the important points of what you need to know to solve projectile problems. So let's get into it. I begin here your special presentation for YouTube. You will see that the whole main idea for projectiles is, circle it here on the right, the strategy is to split a problem into its X part and its Y part. That's step one. And then step two is solve separately. Solve the X problem, solve the Y problem. And then if you need to report something in its vector form, magnitude and direction, you can combine those answers back, the X part and the Y part, combine back into magnitude and direction. Okay, so that's the recipe. And that's really the main idea. That's what we do to solve pretty much any problem. If you want to review how to solve the up and down problem subject to gravity, that's my 2-2 episode here in Rapid Review. And also, if you want to remind yourself how vectors are done in 2 dimensions, 3-3 might be helpful. So you can review those if you have not seen them before. Now that you know the main idea, it's time to look at the equations. You have seen these equations so many times before. It's really just one set of equations. It's, you know what, I'm going to call it 3 equations. I never really use this V-average thing anymore. I just do it because that's what it was in the textbook when I first wrote these down. But I find I use 3 equations, and of course these equations, the X version and the Y version, that is the horizontal and the vertical versions of these, it's the same. It's just that one uses the letter X and one uses the letter Y. And you know it's perfectly okay to do that, right? As long as you have constant acceleration in one dimension, those are the equations, okay? So remember when you use these equations that if you're talking about horizontal motion here on the surface of the Earth, there is no acceleration. And if you're looking at vertical motion, acceleration, of course, is g, negative 9.8, call it 9.81 if you care to, meters per second squared. That's a negative, right? Okay, so that's it. That's the whole deal. It's all the same equations. Now what's interesting about these equations is the one little hook is that they communicate with each other. They communicate by way of time, because if you look at the equation, you'll see they both refer to time. There's that time all over the place, and that's the same time for X and Y. So because it's all the same time, you can solve one dimension and then work on the other one for a while. For example, I give an equation here, or an example here, where there's a horizontal launch, and maybe you know the initial velocity, and you know the height of the table, and it gets launched off, and you're off and running. You've probably done problems like this. First you do the Y, and you can find time and air for that, and then you do the X, and you can find delta X, the range. And what you can see in the slide here is that the time and air is the same in both, right? So you use one to get time and air, then you work your way through to find delta X. You use one result to find the other. Now, I say classic solving tip. When in doubt, go for time first. If you look at that, put that up on your wall, put that in your notebook. It's not a universal law of physics, but actually my students and I have found it's pretty useful for solving multi-part problems. Often you need to solve for time, which is great because then you have an answer that applies to both x and y because time applies to both of them. When in doubt, go for time first. You might also remember, it's almost like poetry, isn't it? A statement we've made earlier, which is speed is just the magnitude part of velocity. And it's relevant to this conversation here because when you're doing a problem, you have to make sure you're paying attention to whether it's the speed, that is the magnitude part of velocity, or whether it's the components that you're interested in. And for just about all of the problems you're going to be doing, you need to use the components. Okay, so let's look at this, right? First step, remember I said step one is convert any magnitude and direction into components, then you're off and running. And you use those components in all of your calculations. Do not be tempted to use the magnitude of velocity, otherwise known as the speed. Do not use that in your x or y calculations. You need to use the components. Common mistake, easy mistake to make. Be careful, right? The speed here, I might also call the full magnitude of the original velocity or of any velocity vector. I called it m in the picture for magnitude. You can call anything you want. If you choose to call it total velocity, like v sub t, be careful if you use that notation. I've seen that notation in some resources. Be careful about total velocity. If you want to think about that as, if you want to use that notation to express the speed of a vector, the magnitude part of the vector, be careful that if you're ever trying to combine components together, it's not just, as I show here, it's not just take the magnitude of x and y components and add them together to get a total. It's not that at all because, of course, v sub x and v sub y are two components of a vector. And if you want to create a so-called total velocity, you got to be careful and use vector addition there, which you know how to do. Okay, so probably said more than I need to there, but it's worth emphasizing. While I am talking about pitfalls, watch out for this one. Do I dare show it? I'll show it. Okay, the range equation. I put a big exclamation point there, and I don't even put the equation for you just because it has led to confusion for students. There exists, you've probably seen, a special equation, special case for ground to ground or tabletop or whatever you call a projectile that starts and ends from the same place, right? It only works for that. And if you don't care about time, you can use that to find the range. We call it the range equation. It does use the speed, so if you ever see the range equation, it's okay to use the original full magnitude of the starting velocity because that's part of the equation. I have one more thing I want to show you too, is another common pitfall, or especially in the beginning. Somebody says, what is the speed of the projectile when it lands? Every once in a while, a student will say, well, it's 0 because it landed. It's on the ground, right? So it's 0. And that's not what we mean when we say when it lands. I know it's kind of sloppy vocabulary, but what we're talking about is the period for the projectile, the period in which the acceleration is constant. So if I throw this, like all this pushing I'm doing and stuff, not constant acceleration. But once I let it go, it's a projectile, and it has constant acceleration all the way down to the time just before I catch it, just before. And that's what I mean. When I say when it lands, I mean just before it lands, okay? So think carefully about what that means. If you see something like, I made a list here, like when it lands, or when it is caught, or at impact, those kinds of phrases all mean, really, they mean just before it lands, okay? So I think that might be all I have to say. Oh, it is, because your next move will be to practice, if you haven't done already. Solving problems in projectiles takes practice. It's just getting familiar and getting used to it and building up your intuition, how to approach a problem, and so on. Also, labs are an important part of learning this topic. And how can I forget? One last thing, playtime. If you want to play around with a simulator, I recommend this simulator from PHET. It's shooting things out of a cannon, and you can control parameters like, oh, I don't know, you can control like what you're launching and what the launch angle is and what the height is. It's a good way to get familiar with how all this stuff works. You can even turn on vector notation and see arrows pointing out of your projectile as it moves, and you could see the magnitude and direction of various vectors. Definitely worthwhile. I'll put a link to that in the comments. I don't have any more to offer you here. Go enjoy, play around with projectiles, see what you can do, and I'll see you in the next episode.